Good evening, everyone. Good evening, good evening, good evening. I welcome you all again to the JEE Enthuse. Hope all of you are doing great, having the good time at home. Well, people, if I'm audible and visible to everyone, hit the chat box with the thumbs up. Let me know if I'm audible and visible to everyone. Yes. Hi, Nishant. Hi, Navneet. Hi, Kirito. Hi, Uncharted. Hi, Sahana. Hi, Amir. Good evening, good evening, good evening. Welcome back, guys. Welcome back to the Chemical Equilibrium Part 2. Yes. Navneet has come up with the quote of the day. It seems winning does not always mean being first. Okay, Navneet. All right. I get it. I get it. Nishant, मैं बिल्कुल बढ़िया. आप कैसे हो? I'm doing wonderful. All right, guys. All right. So let me tell you, in the today's session, we are going to continue with the chapter which we started in the last session. The name of the chapter is Chemical Equilibrium, right? And today is going to be our second session on Chemical Equilibrium. Yes. Good evening, Aishwarya. Good evening. Hi, Padma. All right. So before starting the session, let me introduce myself. As you all must be knowing now, my name is Wassim Sir and I'm your chemistry master teacher right here. Okay. So people, before starting, let me show you the schedule of the week, which I always show in the every session. Let me tell you, today we are going to do the Chemical Equilibrium Part 2, and this whole week I'll be doing the Chemical Equilibrium. Yes, we are going to talk about the Chemical Equilibrium in detail, guys. Okay. In detail, I'm going to talk about the Chemical Equilibrium in this whole week. Yeah. All right. Talking about the Menti quiz, guys. On Tuesdays, you have got Menti with your own favorite, Shimon Sir. Yes. And it's from the coordinate geometry, which involves your parabola, ellipse, and the hyperbola. On Thursdays, it's with the Shreyas Sir. Okay, I know you guys are super duper excited for that session as well, because he's taking the Menti session from the capacitors part. Yeah. And people, on Sunday at 9 p.m., I'll be taking the Menti session from the chapter which is currently going on, which is your Chemical Equilibrium. Yes. All right. So people, before starting, do not forget to like the video, share and subscribe at the same time so that everyone will get benefited out of these sessions. Yes? Okay. All right. Uncharted, it's going to be the full chapter. I'm going to finish the Chemical Equilibrium in this current week. Yeah? On Sunday, it's going to be the Menti from that. All right. Welcome Adi. Welcome Vignesh. Welcome everyone. Welcome Shahid. All right, guys. All right. So before starting the session, let me give the brief introduction of the Vedantu JEE Pro subscription. If you guys are getting enrolled in the Pro subscription, what all benefits you guys are going to get? Let me tell you, you guys are going to get 5,000 plus hours of live online teaching. Regular tests and assignments will be provided to you, which contains more than 10,000 questions. We have got 20 plus teachers with 5+ years of experience who will be training you personally for the upcoming JEE 2021 as well as JEE 2022. And let me tell you, you have got complete liberty to learn either in English or in Hindi. It's completely your wish to select the language, get trained by the master teachers of Vedantu in your physics, chemistry and mathematics. Right, for the upcoming JEE 2021 or your JEE 2022. And let me tell you, in the Pro subscription, we are going to cover everything which includes your micro as well as crash courses. Yes. Thank you, Nick. Thank you. Einstein, you're not late. I didn't start yet, bro. Chill. All right, guys. All right. So for the ones who are going to appear in the JEE in 2021, we have come up with 3 different plans for you. Okay. And people, the best part is on every plan you have got 50% off. Okay, so check it out. It's 50% off on whatever plan you'll be selecting right now. Okay, let me tell you, the 1 month plan, after the 50% off, you guys are just getting it for 3,750. 3 month plan 10.5k, 6 month plan 27k. For the ones who are going to appear in the JEE in 2021, on all the plans you have got 50% off right here, guys. Okay, so do check it out. For the ones who are going to appear in the JEE in 2022, we have come up with 4 different plans for you, as you all can see. The first plan, which is the 1 month plan, 3 month plan, 6 month, 12 month, and on every plan you have got right here the 50% off. Yes, 1 month plan, you guys are just getting it about 2,500. That's it, guys. That's it. 3 month plan 6.75, 6 month plan 12k, 12 month plan 21k, and all these plans are valid for the ones who are going to appear in JEE in 2022. Yes, so how to get these plans, guys, how to get enrolled in the actual Vedantu platform through these plans. Let me tell you, there's a link in the description box. You guys just have to click on that link and use the coupon code as WBPRO. Yes, on using this coupon code of WBPRO, you guys are going to get 50% off on whatever plan you're selecting for yourself, right? All right, so let me know, guys, if you're super duper excited for this session. Let me know in the chat box if you are super duper excited for this session. Yes, let me know in the chat box if you are super duper excited for the session. Good evening, Darshini. Good evening. Thank you, Nick. Thank you. Let me know in the chat box if you guys are super duper excited for the today's session. Yes. Hit the thumbs ups. Let me see the josh of the session. Yes. Navneet is damn excited about the session. Kirito is super excited. Sana is super excited. Wonderful. What about the rest of the people? Are you super duper excited for the session, guys? Yes. That's wonderful. All right then. So let's get started with the today's discussion. So first of all, I'll be giving you the relation between Kp and Kc. Yes. I'll be giving you the relation between Kp and Kc from which the equations frequently come into your examination, right? Alright guys, so first of all, let's try to get the relation between Kp and Kc and then I'll show you how to apply the relation in the equations, okay? So let's get started. Relation between Kp and Kc, alright? First of all, right here, I'll be taking one homogeneous gaseous phase reaction. I'm taking a homogeneous gaseous phase reaction. Let's say I'm taking the reaction as N1A, which is in gaseous form, plus N2B, which is in gaseous form. Again, it is in equilibrium with N3C, which is again in gaseous form. Yes, plus N4D, which is again in gaseous form, right? First of all, as you all can see, A is in gaseous state, B is in gaseous state. I mean, this, just a second, what happened to this? Okay, this is C, all right. This C is also in gaseous state and D is also in gaseous state, all right. Whenever you'll be having such kind of a reaction in which all the reactants and products will be present in the same state, we call it as the homogeneous reaction. Since all the reactants and products are in gaseous state, so I'll be calling this reaction as the homogeneous gaseous phase reaction, right? Now people, in the last session I told you, for gases particularly, we define two terms. For gases, we define two terms. Yes, we define two terms. One is the pressure of the gas, which we call as partial pressure of the gas, and the second one is the concentration of the gas. For the gas, we define both the terms, pressure as well as concentration, right? Now people, first thing, if I want to write the expression for Kp right here, if I want to write the expression for Kp, which I showed you in the last session, how to write it for different reactions. Yes, so Kp is going to be, I'll be starting from the products, I'll be writing partial pressure of C at equilibrium to the power N3, which is the stoichiometry coefficient of C, multiplied by partial pressure of D at equilibrium to the power stoichiometry coefficient, that is N4, divided by what? Divided by partial pressure of A to the power its stoichiometry coefficient N1, multiplied by partial pressure of B at equilibrium, multiplied by stoichiometry coefficient of it, that is N2. This is how I'll be writing the expression for Kp. Yes. Similarly, guys, you can write the expression for Kc as well. Yes, and whenever you write the expression for Kc, let me tell you, you have to replace the active masses by the term concentration. Yeah, very simple. So Kc I can write concentration of C at equilibrium to the power N3 multiplied by concentration of D at equilibrium to the power N4, which is the stoichiometry coefficient of D, divided by concentration of A at equilibrium to the power N1 multiplied by concentration of B at equilibrium to the power N2. Yes, very simple. Now people, this reaction is taking place in a container. Yes, it will be taking place in a container, and all the reactants and products, they are present in the gaseous state. Yes, so people, as per the ideal gas equation, we know PV is equal to nRT. Absolutely, yes. I can write it like this. P is equal to N divided by VRT. Yes, I can write it. Now, number of moles divided by volume. Do we call this term as concentration? Yes, we call it as concentration multiplied by R multiplied by T. So I got the general result over here. P is equal to concentration multiplied by R multiplied by T. If I'll write over here PA, if I'll write for example PA, so what do you think PA will be equal to? PA will be simply equal to concentration of A multiplied by R multiplied by T. Similarly, if I'll write the term PB, partial pressure of B, it's going to be concentration of B multiplied by R multiplied by T. Similarly, PC is going to be concentration of CRT. Similarly, PD is going to be concentration of DRT. Yes, very, very simple. Now we will understand. See, I got an expression right here, which is the Kp expression, which I got to know as partial pressure of C at equilibrium. Instead of partial pressure of C at equilibrium, can I write concentration of C multiplied by R multiplied by T? Yes, to the power what? To the power n3. Absolutely, I can write it to the power n3 multiplied by this PD is partial pressure of D, which is going to be concentration of D multiplied by R multiplied by T raised power its stoichiometric coefficient, that is N4 divided by what? This is partial pressure of A, which is going to be concentration of A multiplied by R multiplied by T. Yes, to the power what? To the power N1 multiplied by concentration of B multiplied by R multiplied by T to the power what? To the power N2. I can say that, yeah, I can write it like this, very, very simple. Okay, now people have a look. Have a look. Understand properly what I'm going to say. See guys, it's a very simple concept. I'll be writing Kp over here as, this is concentration of C to the power N3. Then we have got concentration of D to the power N4. I'm writing it as such. Concentration of, just a second, it's concentration of C, yes. So I'll be writing concentration of C to the power what? To the power N3 multiplied by. Then I'm writing concentration of D to the power N4 divided by concentration of A to the power N1, concentration of B to the power N2. Yes, it's going to be concentration of A to the power N1 multiplied by concentration of B to the power N2. And over here we have got RT to the power N3, RT to the power N4. Yes, and in the denominator we have got RT to the power N1, RT to the power N2. So I'm going to write RT in common, yes, and RT to the power. This is going to be N3 plus N4 minus N1 plus N2. Yes, I can write it. This is going to be N3 plus N4. N3 plus N4, or let me erase this part so that I can get a space over here. Yes, I hope you would have written it. Okay. Now let me write it like this. So this is Kp will be equal to this part multiplied by RT to the power N3 plus N4 minus N1 plus N2. Yes. Now people, first thing, if I want you guys to write the delta Ng value for this reaction, what will be the value of delta Ng for the reaction which I have written over here? Very, very simple. Say guys, delta Ng is going to be number of moles of gaseous products minus number of moles of gaseous reactants, which we have discussed in the thermodynamics as well. So number of moles of gaseous products are going to be N3 plus N4. It's going to be N3 plus N4. Let me write it somewhere here, just a second, or let me erase this part here. Yeah, I can write it N3 plus N4 minus number of moles of gaseous reactants, which will be N1 plus N2. And over here, if you can see, I got the same thing, so I can replace it simply and I'll get an expression right here, which is very, very important and which I want you guys to remember right here. It's going to be Kp equaled. People, what do we call this thing as? This thing is what we call as Kc. Yes, so it's going to be Kp is equal to Kc RT to the power what? To the power delta Ng. Yes, because N3 plus N4 minus N1 plus N2 is delta Ng. This is the relation between Kp and Kc for a given reaction which you will be having, which will be present at the equilibrium. Yes, let me know in the chat box if it is clear to you. Kp is equal to Kc RT to the power delta Ng. This is the relation between your Kp and Kc. Yes, good evening Sakshi, good evening. Yes, wonderful guys, great. All right, a lot of people are saying it's clear, it's damn clear. Yeah, that's actually great. Now moving ahead, and let me give you one more relation over here about it. Let me give you one more relation right here. Just understand that as well. So people, see, I got the relation as Kp is equal to Kc multiplied by RT to the power delta Ng. This is the relation between your Kp and Kc. Yes, where delta Ng you can calculate for any reaction. All right. Now one more thing, if I want to write the logarithmic form of this reaction, this equation, what I'll be doing, I'll be simply multiplying the equation by log. It's going to be log of Kp is equal, this is going to be log of Kc plus log of RT to the power delta Ng. This is something this is how I'll be writing it. Yes, I simply multiplied it by log, then it became log of m into n, which is log of m plus log of n. Yes. Alright guys, so log of Kp I got equal to as log of Kp, I will get the final result in the form of log. It's going to be log of Kp is equal to log of Kc plus this is going to be delta Ng multiplied by log of RT. This is something which I got right here. This is the logarithmic form of this Kp-Kc relation, correct? This is the actual relation and this is its logarithmic form. Yes. Now people, first thing which I would like to share with you right here, if I will plot a curve between log P versus log RT. If I'm plotting a curve between log P versus log of RT, what do you think will be the nature of the curve? I'm plotting log of RT along x-axis, I'm plotting log of P along y-axis. So can I say instead of log of P, I'll be writing simply y is equal, instead of log of RT, what I'll be writing? I'll be writing simply x, because I'm plotting log of RT along x-axis, and before x we always write m, where m is the slope, and m over here is your delta Ng, and over here you got the plus sign, and log of Kc is nothing, it is just the intercept. Y is equal to mx plus c. Can I say the curve is going to be a straight line, but the straight line won't be passing through the origin, it will be starting above from the origin. Yes, so the curve will be somewhat like this. Yeah, this is going to be the curve. And people, if I'll ask you what will be the slope of this curve, slope of this curve is represented by m. Yes, m is what we call a slope, and slope of this curve, that means the value of m right here is actually the value of delta Ng. So from this curve guys, you can easily get delta Ng value whenever you'll be given with this sort of a curve. Yes, very, very simple. And at the same time, if I'll ask you about this intercept, what will be this intercept all about? This intercept means the value of c, and the value of c right here is nothing, it is just log of Kc. I'm sure this is clear to everyone. Let me know in the chat box if it's clear to you. Yes, let me know in the chat box if it's clear to you. Guys, let me tell you, this is not log of P, this is log of Kp, okay? This is log of Kp. I forgot to write K right here. This is log of Kp. Log of Kp versus log of RT. Yes? Yes? Wonderful, guys. Great job done. Let's move on. I hope you have copied all this, alright? I'm moving on to one more thing over here. Right here. That is the relation between Kp and Kx. The relation between Kp and Kx. Correct? The relation between Kp and Kx. Let's talk about this relation as well. So first of all, guys, as you all must be remembering, your equilibrium constant we classify into, we divide it into three parts. One is called as Kc, one is called as Kp, and one is called as Kx. Yes, whenever in the expression of equilibrium constant, we replace the active mass by the concentration, at that time we call this Keq as Kc. Whenever in the expression of equilibrium constant, we replace the active masses by the partial pressures, we call it as Kp. And whenever in the expression of equilibrium constant, we replace the active masses by the term mole fraction, we call it as the Kx at that time. Yeah, and now it is the time to get the relation between Kp and Kx. All right, let's say I've got a relation like this. Let's say I've got a homogeneous gaseous phase reaction like this, N1A gas in equilibrium with N2B gas. Let's say this is the homogeneous gaseous phase reaction which I have right here. Now people, I can write its Kp expression as well as I can write its Kx expression. Yes, its Kp expression is simply going to be partial pressure of B at equilibrium to the power stoichiometric coefficient divided by partial pressure of A at equilibrium to the power stoichiometric coefficient, that is N1. Yes, And at the same time, if I want to write the expression for Kx, it's going to be mole fraction of B at equilibrium to the power n2 divided by mole fraction of A at equilibrium to the power n1. This is the Kx expression. This is the Kp expression. Yes. Now people, very simple thing. If you remember, in the last session, what did we discuss? We discussed at time t is equal to 0, when the reaction has not started, I'll be only having moles of A in the container in which this reaction will be taking place. Yes. So can I say at time t is equal to 0, whatever pressure will be there in the container, whatever pressure will be there of the container, that will be only due to A at time t is equal to 0. Yes. And at the same time, if you'll see, the number of moles of reactants with time will decrease and number of moles of products with time will increase. So can I say, if the number of moles of reactants with time are decreasing, can I say pressure, the total pressure of the container due to A will be decreasing at the same time, right? And the total pressure of the container due to B will be increasing with time. Okay, once equilibrium is established, the partial pressure of A and B will become constant, will become fixed. Yes, we have discussed that in detail in the last session, if you remember. Yeah. Now people see, if you remember, in the gaseous state we have discussed the Dalton's law of partial pressure. Can I say the total pressure at equilibrium, will be the sum of partial pressure of A and B at equilibrium? Yes. Yes. So people, very simple concept. When equilibrium will get attained in the reaction, number of moles of A and B will become fixed, will be constant. So partial pressure of A, I mean the contribution of A towards the total pressure at equilibrium, and the contribution of B towards the total pressure at equilibrium, they will also attain a fixed value. That means the partial pressure of A and B will attain a fixed value at equilibrium. Yeah. We have discussed that. And can I simply say whatever will be the total pressure of the mixture at equilibrium? Because at equilibrium, I'll be having moles of this as well as moles of this. So at equilibrium, I'll have the mixture of gas, and whatever is going to be the total pressure of that mixture, that will be equal to the sum of the partial pressures of the each gas right here in the container at equilibrium. Yes, very simple. And at the same time, in the gaseous state, we have discussed the partial pressure of A will be equal to total pressure multiplied by mole fraction of A. Similarly, partial pressure of B is going to be total pressure of the container multiplied by mole fraction of B. Yes, very simple. Now people, can I write it like this? Kp will be equal to partial pressure of B at equilibrium. Isn't it going to be total pressure at equilibrium multiplied by mole fraction of B at equilibrium to the power n2 divided by partial pressure of A? It's going to be total pressure multiplied by mole fraction of A at equilibrium to raise power what? Raise power n1. Okay, can I write it like this? P to the power n2 minus n1 multiplied by mole fraction of B to the power n2 divided by mole fraction of A to the power n1. Do we call this term as Kx? Yes, we call it this as Kx. Yes, we do that. Now people, at the same time, what I got the value of Kp as Kx multiplied by P to the power n2 minus n1. Can I say for this reaction n2 minus n1 will be the value of delta Ng? Absolutely. It's going to be n2 minus n1, right? So I can write P to the power delta Ng. This is the expression, this is the relation between Kp and Kx for the reaction which we had. Yeah, let me know in the chat box if it's clear to you. So that I can move ahead and talk about few more interesting things right here. Let me know in the chat box fast. Let me know in the chat box if it's clear to you. Let me know in the chat box if it's clear to everyone right here. Yes. So first of all, I want you guys to remember these two relations. Yeah. Kirito, in the gaseous state, we have discussed, bro, partial pressure of A will be equal to total pressure of the mixture multiplied by mole fraction of A. Yes. When I discussed Dalton's law of partial pressure with you, if you remember. Yeah. All right. Moving on. Let me first of all give you the logarithmic form of this. As well. See guys, I got the relation between Kp and Kx as Kp is equal to Kx multiplied by this P is the total pressure. This P is the total pressure of the mixture at equilibrium. Yes, to the power delta NG. If I want to get the logarithmic form, I'm supposed to multiply throughout by log. Yes. So can I say I'll get the equation like this? Log of P will be equal to log of kx plus delta NG, and this is going to be log of P. Yes, this will be the relation, this will be the expression in the logarithmic form. Yes, these are the two expressions which I want you guys to remember right here again. Okay, now people, at the same time, if I want to plot a curve, and you guys are going to tell me what the curve will look like. If I want to plot a curve, let me erase this part first. Yeah. Okay, if I want you guys to plot a curve between log of Kp versus log of P, where P is the total pressure of the equilibrium mixture. Yeah. Now we will see. First of all, along x-axis, I'm plotting log of P. Along y-axis, I'm plotting log of Kp. So instead of this log of Kp, I can write y. Instead of this log of P, I can write x. And before this x, we have got m, which is the slope of the curve, and m over here is delta ng, and log of kx right here is the intercept over here. Y is equal to mx plus c. Isn't it again going to be a straight line? But the straight line won't be passing through the origin. Because it has got intercept with it. And how much is the intercept? Intercept is simple, the value of c, which is log of kx. Yeah, which is log of kx. And at the same time, if I'll ask you what is the slope of this curve, slope of this curve means the value of m. Value of m right here is equal to the value of delta Ng for the reaction, because from the equation we got the m to be equal to as delta Ng. Yes, let me know fast if it's clear to you. Yes, let me know fast if it's clear to you. Wonderful, guys. I'm erasing this part. I'm sure everything, whatever I've taught you till now is clear to you. I'm assuming that, okay? And I'm damn sure it'll be clear to you, yeah? All right, let's move on and let's talk about few basic questions first. Then we'll be moving ahead and talking about few important things right here, okay? Write the Kp expression for the following in terms of Kc. Yes, very, very simple question so that you can understand these things, these concepts which we have discussed right here. Yes? No, Sony, it's not beyond CBSE level. You can watch these lectures, yeah? I'm starting exactly from the basics, yeah. All right, guys. The first reaction which we have, if I want you guys to calculate delta Ng for the first reaction, what do you think will be the value of delta Ng? Number of moles of gaseous products, which is 2, minus number of moles of gaseous reactants. So over here it's going to be 1 plus 1, that is 2. So delta Ng value I got as 0. If I got delta Ng as 0, we know Kp is equal to Kc RT to the power delta Ng. And since we got to know delta Ng is 0, that means Kp for the reaction will be equal to Kc, right? So this is the first thing. Second reaction which we have, we need to write the expression of Kp in terms of Kc again. Yeah. Now first of all, you check whether the reaction is balanced or not. Absolutely it's balanced. So can I calculate the value of delta Ng for the reaction? Absolutely I can do that. Number of moles of gaseous products, 1 plus 1, that is 2, minus 1. That means I got the value of delta Ng as 1 over here. Absolutely, yeah. I got the value of delta Ng as 1. Now people, you can write the Kp relation. Kp will be simply equal to Kc multiplied by RT to the power 1. Yes, this will be the value of expression for Kp in terms of Kc. Yes, absolutely. What about the third reaction, guys? What about the third reaction? Even third reaction is also balanced. Yeah. What is the value of delta Ng for third reaction? Can I say number of moles of gaseous products, which is 2, minus number of moles of gaseous reactants, which is 1 plus 3, that is 4. 2 minus 4 is minus 2. So Kp value will be simply equal to Kc RT to the power minus 2 over here for the third reaction. Yes. Very, very, very simple. Now people, at the same time, what about the last one? What about the delta Ng for the last reaction? Isn't it going to be number of moles of gaseous products? Since only this is the gaseous product, this is solid, I've got nothing to do with this. This is solid, I've got nothing to do with this. So only gaseous component over here is carbon dioxide. And how many moles of it do we have? Only 1. Yes. So delta Ng value, we got it as 1 for the fourth reaction. If delta Ng you got as 1, I can simply write Kp will be equal to Kc RT to the power 1. This will be the expression for the fourth reaction over here. Let me know in the chat box if it is clear to you so that I can move ahead. Let me know fast. Yes, Kirito, you're right. Yes, yes, absolutely. Absolutely, guys. All right. Moving on to the units of Kp and Kc. Moving on to the units of Kp and Kc. All right. What are the units of Kp and Kc? For that, let me take a reaction as N1A gas in equilibrium with what? In equilibrium with N2B gas. This is the reaction which I have. If I want you guys to calculate the delta Ng for this reaction, it is simply going to be number of moles of gaseous products minus number of moles of gaseous reactants, which is going to be N2 minus N1. I'm sure it's clear till here. Yes. Now people, what about the expression for Kp? Expression for Kp for this reaction is going to be partial pressure of B at equilibrium to the power stoichiometry coefficient divided by partial pressure of A at equilibrium to the power stoichiometry coefficient N1. What about the expression for Kc? I'm sure you can write that too. That's going to be concentration of B at equilibrium to the power N2 divided by concentration of A at equilibrium to the power N1. Yes. Now people, talking about the units. What will be the units of Kp? See guys, over here we have got pressure term, over here we have got pressure term. If I'm talking about the units in terms of ATM, so in the numerator you have got ATM to the power N2, in the denominator you have got ATM to the power N1. So I will get it like this: ATM to the power N2 minus N1, and N2 minus N1 is what we call as delta Ng. So these are the units of Kp which you can write over here. Correct? Knowing just the delta Ng for the reaction, you can talk about the unit of Kp as well. Yeah, very simple. Now people, what about Kc unit? What about the units of Kc? Isn't it going to be concentration at the top in the numerator and concentration in the denominator? How do we define concentration? Number of moles divided by volume. Yes. So what do you think will be the units of concentration? It's going to be moles per liter. Yes, it's going to be moles per liter to the power what? Stoichiometry coefficient, that is N2, divided by over here one more concentration term. So instead of it, I'm writing moles per liter to the power N1. So shouldn't it become moles per liter to the power N2 minus N1, and N2 minus N1 is what we call as delta Ng. So this is how we write the unit of Kc over here. Let me know in the chat box if it is clear to everyone. Sony, it's your wish. You can write that as well. No issues. Aditya, who told it's my birthday, bro? It's not my birthday. All right. Let me know in the chat box, guys, if it's clear to you. Yes. Wonderful, guys. Talking about few more interesting things right here. What are those? Let's talk about these things right here. Then I'll be moving to the actual numerical part of this chapter. I didn't enter into the numerical part of this chapter yet. I'll be entering that once we get done with the basic things. Okay, because those basic things, those are really, really important. You should know those basic things first. Then only you can solve the questions. Yeah. Very, very simple. First of all, talking about the characteristics of the equilibrium constant. Okay, there are few characteristics of equilibrium constant which I want you guys to remember. First thing, it does not depend on the initial concentration of reactants and on the catalyst. Yes, it does not depend on the concentration of initial concentration of reactants. The value of equilibrium constant is independent of the initial concentration of reactants. First thing. Second, the value of equilibrium constant is independent of the usage of catalyst as well. Okay, catalyst has got no role for the value of equilibrium constant, right? Catalyst, what does positive catalyst do? For example, I'm talking about positive catalyst. It speeds up the rate of reaction. It speeds up the rate of reaction. If it is speeding up the rate of reaction, it will, by using the catalyst, what will happen? Equilibrium will get attained quickly in the reaction. That's it. Equilibrium will get attained quickly in the reaction. That's it. Okay, nothing else. So catalyst has got no role to play with the value of equilibrium constant. Yes, and at the same time, equilibrium constant is independent of the initial concentration of reactants, and equilibrium constant only depends on the temperature, which I'll be showing you afterwards. I'll be giving you the relation which will clearly tell you what will happen to equilibrium constant on changing the temperature. Yeah, but right now I want you guys to remember it. Equilibrium constant depends on temperature, right? On changing the temperature, the value of equilibrium constant changes. Yes. Yes, Vishwa, I'll be taking the ionic equilibrium as well. Yes, it also depends on the stoichiometric representation of the reaction. Yes, it depends on the stoichiometry of the reaction as well. Correct? Few basic things, guys. Basic things. When a reaction is reversed, its equilibrium constant gets inversed. When a reaction is reversed, its equilibrium constant gets inversed. Very simple. Let's say I've got a reaction like this, A in equilibrium with B. Let's say its equilibrium constant is K1. Let's say its equilibrium constant is K1. Now people, if I'll reverse the same reaction, it gets B getting converted into A. If I'll reverse the same reaction, on reversing the reaction, the new equilibrium constant for this reaction will be 1 divided by K. So when a reaction is reversed, its equilibrium constant is inversed. Very simple. Similarly, if a reaction is multiplied by some number, that number goes to the power of the equilibrium constant. What do we mean by that? Let's say I've got a reaction as A in equilibrium with B and its equilibrium constant is, for example, K1, correct? If I'm multiplying the reaction by 2, what do I get? 2A in equilibrium with 2B. Now people, the new equilibrium constant for this reaction is going to be K1 ka square. So whatever number you are multiplying with right now, that number directly goes to the power of equilibrium constant. Yes. If you are multiplying it by 3, it becomes 3A gives 3B. So its new equilibrium constant becomes K1 ka cube. Yes. Very simple. Okay. If you are multiplying the reaction by 1 by 2, its new equilibrium constant becomes K1 to the power 1 by 2, which means root of K. Yes. Correct. And remember, at the same time, whenever we add reactions, their equilibrium constants are multiplied. For example, have a look, guys. It's a very simple thing. Let's say I've got the reaction as A in equilibrium with B, whose equilibrium constant is K1. Let's say I've got a reaction, one more reaction, B getting converted into C, whose equilibrium constant is K2. If I'll add these two reactions, this B and this B will get cancelled, and the net reaction which I'll get right here, that is A in equilibrium with C. What about the new equilibrium constant for this reaction? Let me tell you, whenever you add the reactions, their equilibrium constants are multiplied. So a new equilibrium constant becomes K1 multiplied by K2. If you are adding 3 reactions, it would have become K1 into K2 into K3 like that. Yeah, I'm sure this is clear to everyone again. All right, let me know in the chat box if it's clear so that I can move on and talk about few more important things. Let me know fast in the chat box, guys, so that we can do this basic question. This is the first basic question which I've given to you right here. You can easily solve this question, guys. I'm sure about it. Yes. Yes, Abranil, I remember, bro. All right. See, guys, as per the question is concerned, this is a very simple question. Very simple question, provided you remember all the things which I have shown you right here. Okay. See, guys, understand. Kp for the reaction. We are given with the reaction as N2 gas plus 3 times H2 gas in equilibrium with 2 times NH3. Gas. Yes. And we are given with the Kp value for this reaction. Its Kp value is given as 49. Calculate the value of Kp at the same temperature for the reaction. So this is the reaction for which Kp value I have to calculate. Kp value. For the reaction for which I have to calculate Kp value, in this reaction, NH3 should be on left hand side. Okay, NH3 should be on left hand side for the reaction for which I have to calculate Kp value. Yes. So what I'll be doing, I'll be first of all reversing this reaction. On reversing the reaction, I will get 2 times NH3 gas in equilibrium with N2 gas plus 3 times H2. And people, as you all must be knowing, on reversing the reaction, what happens to the equilibrium constant? Equilibrium constant is inversed. So K dash becomes 1 divided by, I'll write it as Kp dash becomes 1 divided by Kp, which is going to be 1 divided by 49. Okay. Now people, this is 2 times, but in my actual reaction, it should be 1 times. So what am I going to do? I'm going to multiply this reaction throughout by 1 by 2. I'm going to multiply this reaction throughout by 1 by 2. If I'll multiply this reaction throughout by 1 by 2, it becomes 1 by 2 into 2. That means NH3. That means NH3 in equilibrium with what? Half of N2 gas plus 3 by 2 times H2 gas. What did I do? I multiplied this reaction by 1 by 2. And if you remember, I told you with whatever number you are multiplying the reaction, that number goes to the power of the equilibrium constant. So I can say K double dash P, new equilibrium constant right here, is going to be simply equal 1 divided by 49 to the power 1 by 2, which is simply going to be 1 divided by 7. This is the reaction for which we were supposed to calculate Kp, and we have calculated it to be 1 by 7. Let me know if it's clear to everyone. Let me know if it's clear to everyone. Fast. I'm waiting for you. Absolutely, Kirito. Absolutely, Darshini. Yes, yes, Ashwarya, you're right. Yes, Vishwajit. Yes, yes, Uncharted. Yes, yes, absolutely. Yeah. Let me know in the chat box if it's damn clear to everyone. Yeah. Wonderful, guys. Great. Great, great, great. Moving on then. Moving on to some important things which we have to discuss now. Okay, that is KP-KC calculation, which is really very important. From this topic, your actual equilibrium starts. Okay, KP-KC calculations, guys. Okay, you have to understand few basic things which I'll be telling right now. Okay, if you remember those things, you can easily solve any question from this KP-KC calculation part. Okay, and this is going to be interesting and fascinating at the same time. Okay, understand, guys, and remember at the same time. In order to calculate the Kp and Kc for different reactions, we have got two methods to get the value of Kp and Kc for a reaction. The first method is what we call as mole method. Second method is what we call as degree of dissociation method. Okay, these are the two methods with me by means of which we can calculate Kp and Kc for different reactions. Correct? And in the today's session, I'm going to start with the mole method. And I won't be able to finish the mole method completely. In the next session, we'll be continuing with the mole method, and in the next session, we'll be starting with the degree of dissociation method as well. Right? Okay, let's talk about the mole method right here. Let's talk about the mole method first of all, and I am going to take the reaction first of all for which delta Ng is 0, correct? This is the reaction which I have taken over here, and for this reaction, if you want to calculate, you can calculate the value of delta Ng, which will come out to be 0, yes, which will come out to be 0, yes, very simple. Now we will see what am I going to do. First of all, I need to get the expression for Kc. I need to see what Kc for this reaction will look like, okay? What Kc for this reaction will look like. First of all, Kc will be equal to concentration of H2 at equilibrium to the power stoichiometry coefficient multiplied by concentration of I2 at equilibrium to the power stoichiometry coefficient divided by concentration of Hi at equilibrium to the power stoichiometry coefficient. Yes. Stoichiometry coefficient is how much? Stoichiometry coefficient is 2. First of all, I should know what are the concentrations of H2, I2 and Hi at equilibrium. And how do I get that? How do I get that? Janan, in the NEET Lead channel, we are starting redox reactions, okay? Tonight, I'll be starting the redox reactions there on NEET Lead channel, okay? See guys, see how to approach these sort of questions. First of all, I've taken the reaction for which delta Ng is 0. Okay, this is the reaction which I have. And people, Kc expression, concentration of this divided by concentration of this at equilibrium. Yes. So first of all, in order to write the expression for Kc, what am I supposed to do? I'm supposed to calculate the equilibrium concentration of each reactant and product right here. Okay. Now we will understand. Yes, Aishwarya, you're right, absolutely. Now we will understand. Let's say I'm writing over here time t is equal to 0. Time t is equal to 0. At that time, reaction has not started, correct? At time t is equal to 0, reaction has not started. If the reaction has not started, let's assume I have got A moles of reactant at this time. I'll be having 0 moles of this. I'll be having 0 moles of this. Yes. Now people, what is going to happen? What is going to happen? When the reaction will start, number of moles of reactant will start to decrease, and there'll be a stage which we call as equilibrium stage. Let's say at equilibrium, when equilibrium is attained in the reaction, let's assume at equilibrium, out of A moles of reactants, X moles have got converted into products. If out of A moles of reactant, X moles have converted into product, so I'll be left with A minus X moles of this reactant at equilibrium. These are the moles of Hi at equilibrium, because I'm assuming out of A moles of reactant, X moles have got converted into products, so I'll be left with A minus X moles of reactant at equilibrium. Yes. Now we will understand. Now use the stoichiometry. See how do I use the stoichiometry? See guys, can I say 2 moles are giving me 1 mole? Can I say 2 moles are giving me 1 mole? 1 mole should give me 1 by 2 mole. So X moles should give me X by 2 moles of H2 right here. Yes. Yes. Now people at the same time, 2 moles are again giving me 1 mole. So 1 mole of Hi should give me 1 by 2 moles of I2. So X moles should again give me X by 2 moles of I2. Yes. So people, I got the moles of each reactant and product at equilibrium. These are the moles of reactant and products at equilibrium. Yes. And people, if you remember, in the expression of Kc, do we need the moles of reactants and products at equilibrium, or do we need the concentration of reactants and products at equilibrium? We definitely want concentration of reactants and products at equilibrium, and as you all must be knowing, concentration is nothing, it is number of moles divided by volume. Yes. Now people, first of all, the reaction is taking place. The reaction will be taking place in the container. Let's assume the volume of the container right here. Let's assume the volume of the system right here is V liters. Let's say the volume of the system right here is V liters. Correct? I got the moles of reactants and products at equilibrium. Now people, if I'm dividing these moles by the volume of the system in liters, I'll be getting the concentration. I'll be getting the concentration of each reactant and product at equilibrium. This is the concentration of HI at equilibrium. This X divided by 2V becomes the concentration of H2 at equilibrium, and X divided by 2V again becomes the concentration of I2 at equilibrium. Yes, absolutely. Since I got the concentration of each reactant and product at equilibrium, I can simply write the expression for Kc. Isn't it going to be concentration of H2 at equilibrium, which is X by 2V, multiplied by concentration of I2 at equilibrium, which is again X divided by 2V, whole divided by concentration of Hi at equilibrium, which is A minus X divided by V ka whole square. A minus X divided by V ka whole square. Yes, I'll be getting the value of Kc from here. This is going to be X square, this is going to be 4V square, V square will be cancelled. So I'll get the answer as, I'll get the value of K square as X square divided by, this is 2 2s are 4, multiplied by A minus X ka whole square. This is the value of Kc which I got right here for the reaction. And people, since for this reaction delta Ng is 0, and we already know the relation between Kp and Kc, Kp is equal to Kc RT to the power delta Ng. Since for this reaction delta Ng is 0, so anything raised power 0 is 1. So whatever will be the value of Kc, same is going to be the value of Kp for the reaction. Yes, so this value is for Kc as well as Kp. Correct? Correct? Let me know in the chat box if it's clear to everyone so that I can move ahead and talk about a few more things. Yeah? Walaikum salam, Tabia. Walaikum salam. Let me know in the chat box if it's clear to everyone. Wonderful, guys. Great. Now, first of all, I have shown you how do we write the You're not supposed to remember this expression. You're not supposed to remember this expression. You should know how to write this expression. You should know how to write this expression. So I've showed you the procedure. I've shown you the procedure right here to calculate, to get the expression for Kc. Now I'll show you the expression. I'll show you the procedure by means of which we will be always getting the value of Kp. Okay. If I'm supposed to calculate the value of Kp for the reaction, okay, which procedure I'll be following? The procedure which I followed right here, that will be to calculate the expression for, that will be applied to calculate the value of Kc. Now, if I want to calculate the value of Kp for the same reaction, which I already know should be this much, right? What is the procedure which I need to follow? Understand that as well, right? Let me erase this part, guys. I'm sure this is clear to everyone. I'm sure this is clear to everyone. Yeah? I'm sure this is clear to everyone. Correct? Now, first of all, before starting the procedure, this reaction is first of all taking place in a container, as we all must be knowing. Yes, it is taking place in the container. If I want to write the expression for Kp, expression for Kp is going to be partial pressure of H2 at equilibrium to the power stoichiometry coefficient, that is 1, multiplied by partial pressure of I2 at equilibrium to the power 1, divided by partial pressure of Hi at equilibrium ka square. Yes, this is the expression for Kp. What is this P of H2? This is the pressure. This is the partial pressure of H2 at equilibrium. So first of all, in order to get the Kp expression, I should know what are the partial pressures of reactants and products at equilibrium. Yes, this is something which we should know first. Okay, let's try to get that. Let's try to get that. Understand properly, which I'll be saying. As per Dalton's law of partial pressure, if you remember, partial pressure of a component is always equal to total pressure multiplied by mole fraction. Do you remember this? Yes. Do you remember this? Absolutely, as per Dalton's law of partial pressure. Now see, guys. Now see. At time t is equal to 0, let's assume again I have got A moles of Hi at time t is equal to 0. So this is going to be 0, this is going to be 0. And at equilibrium, I'm assuming out of A moles of reactant, X moles have got converted into products. So I'll be left with A minus X moles of reactant at equilibrium. Now use the stoichiometry simple. 2 moles are giving me 1 mole. 1 mole of Hi should give me 1 by 2 moles. So X moles should give me X by 2 moles. Yes. Yes, very simple. Now people, at the same time, 2 moles are giving me 1 mole. 1 mole of HI should give me 1 by 2 moles. So X moles should give me X divided by 2 moles of I2 right here. Can I say I got the value of, can I simply say I got the value of what? I got the value of moles of each reactant and product at equilibrium. Yes. I got the moles of each reactant and product at equilibrium. Correct? Since I got the moles of each reactant and product at equilibrium, people, can I get the mole fraction of each reactant and product at equilibrium? Absolutely, I can do that. First of all, let's try to calculate total moles which I have at equilibrium. Let's say how many total moles are there in the container at equilibrium. Isn't it going to be A minus X? Isn't it going to be A minus X plus X by 2 plus X by 2 plus X by 2, right? So at equilibrium, how many moles do I have? At equilibrium, how many moles do I have? This X by 2 is X, X gets cancelled. So at equilibrium, I have got total A moles in the container. Yes. Now people, I'm dividing this term by A, I'm dividing this term by A, I'm dividing this term by A. So what did I get right here? I got right here something right here which is called as mole fraction of each reactant and product over here. Yes. I got the mole fraction of each reactant and product right here because I have divided the number of moles of each reactant and product by the total moles which are present at equilibrium. Yes? Are you getting it, guys? Is it clear to everyone? Yes? Very, very simple. I got the mole fraction of each reactant and product. Now people, let's assume at equilibrium, when there is equilibrium in the reaction, let's say at that time the total pressure of the container is P. Let's say at that time the total pressure of the container is P. If I'll multiply this term by the total pressure, if I'll multiply this term by the total pressure, if I'll multiply this term by the total pressure, can I say over here this term is giving me the partial pressure of HI at equilibrium, this term is giving me the partial pressure of H2 at equilibrium, and this term is giving me the partial pressure of I2 at equilibrium. Yes? Since I got the partial pressures of each reactants and products right here, I can simply write the expression for Kp. As you all must be knowing, Kp will be equal to partial pressure of H2. Partial pressure of H2 is nothing, that is X divided by 2A multiplied by P multiplied by partial pressure of I2, which is again X divided by 2A multiplied by P whole divided by partial pressure of HI raised power 2. Yes, because the stoichiometric 2 over here is, stoichiometric coefficient is 2 over here. So I'll be getting, this is A minus X divided by A multiplied by P ka whole square. Yes, so can I get it like this? This is going to be X square, this is going to be X square, this is going to be P multiplied by V, that is P square. Over here I have P square gone, cancel. This is A. So over here I'll be getting A square, this is over here A square gone. So I'll be left with X square divided by 4 multiplied by A minus X ka whole square. Can I say I got the same expression for Kc as well? And I told you in the beginning itself, for the reaction whose delta Ng is 0, for that reaction Kp value will be always equal to Kc. Yeah? Let me know in the chat box if it's clear to everyone fast. Let me know in the chat box if it's clear to everyone fast. Yes, Vishwajit, exactly. All right, wonderful guys. Let's move on to the first question which we have over here on your screen. You can have a look and let's try to solve this question, guys. It's a very simple question provided you got the concept. Yeah. For example, I'm given with the reaction. Right here, which is A gas plus B gas in equilibrium with 2 times C gas. This is the reaction which I have. Now at time t is equal to 0, I'm given with something. Understand the question and read the question carefully. At time t is equal to 0, I'm given with 2 moles of A. So at time t is equal to 0, I've got 2 moles of A, 1 mole of B, 1 mole of B and 1 mole of C. So at time t is equal to 0, when the reaction has not started, I'm given with 2 moles of A, 1 mole of B and 1 mole of C. Correct? Are placed in a 10 liter of vessel. The vessel, the container in which the reaction is taking place, volume of that vessel, volume of that container is 10 liter, is allowed to expand and is allowed to reach equilibrium. If the final concentration of C is 0.2, final concentration of C, that means the concentration of C at equilibrium. This is the concentration of C at equilibrium, which is given to me as 0.2. Yes, then calculate the value of Kc. First thing which you should know, Kc will be simply equal to concentration of C at equilibrium to the power what? To the power 2 divided by concentration of A at equilibrium to the power 1 multiplied by concentration of B at equilibrium to the power 1. This is the expression for Kc which I should use, correct? But before using this expression, I should know what is the concentration of C at equilibrium. I should know what is the concentration of A at equilibrium. I should know what is the concentration of B at equilibrium. Yes. Absolutely. Now we will see. Let's assume at equilibrium. Let's assume at equilibrium, out of 2 moles of A, X moles have reacted with B. Let's say out of 2 moles of A, X moles have reacted with B. If out of 2 moles of A, X moles have reacted with B, can I say at equilibrium I'll be left with 2 minus X moles of A? Correct? Correct? Since from the stoichiometry of the reaction, 1 mole of A reacts with 1 mole of B, so X moles of A should react with X moles of B. So people, I had 1 mole of B and I got to know from this 1 mole of B, X moles are reacting. So I'll be left with 1 minus X moles of B at equilibrium. Yes, isn't it? Isn't it very simple? Yes. So I'll be left with 1 minus X moles of B at equilibrium. Very simple. Yeah? Yeah? Now people, at the same time, see, already at time t is equal to 0, I had 1 mole of C. Already at time t is equal to 0, I had 1 mole of C. Now from this reaction, few amount of C will still get formed. Yes, 1 mole is giving 2 moles. So X moles will give 2X moles. So it is going to be 1 plus 2X. 1 plus 2X are the moles of C at equilibrium. I got the moles of all the components at equilibrium. Yes, since I got the moles at equilibrium, first of all I'll be dividing all these moles by the volume of the container. What I'll be getting? I'll be getting the concentration of each reactant and product at equilibrium. What is the total volume in which the reaction is happening? 10 liters. I'm dividing everything by 10 right here. This term is giving me this 2 minus X divided by T divided by 10. This is the concentration of A at equilibrium. This is the concentration of B at equilibrium, and this is the concentration of C at equilibrium, right? And in the equation itself, the final concentration of C, that means the concentration of C at equilibrium, it's given to me as 0.2. Yes, and from here the concentration of C is nothing, it is 1 plus 2X divided by 10, which is equal to 0.2. Yes, so can I say 1 plus 2X will be simply 2? Yes, so X will be simply equal to 1 divided by 2. I got the value of X as 1 by 2. People, if you got the value of X, so I can put the value of X in these concentrations right here. So over here, I'll be getting the concentration. I'll be getting the concentration of each reactant and product at equilibrium as, put the value of X as 1 by 2. Yes, so this is 2 minus 1 by 2. 1 by 2 is how much? That is 0.5. Yes, 2 minus 0.5, that is 1.5. 1.5 divided by 10, that is 0.15. So 0.15 is the concentration of A at equilibrium. Similarly, 1 minus 0.5, that means 0.5. 0.5 divided by 10, that is 0.05. This is the concentration of B at equilibrium. Now, what about the concentration of C at equilibrium? What about the concentration of C at equilibrium, which is given to me as 0.2, which is given to me as 0.2, okay? Or you can check it out as well. Put the value of X as 0.5. Put the value of X as 0.5 over here. If I'll put the value of X as 0.5, 2 into 0.5 is 1, 1 plus 1 is 2, 2 divided by 10 is 0.2, which we already knew. Yes, so I got the concentration of each reactant and product at equilibrium. If you get the concentration of each reactant and product at equilibrium, you can simply use the expression for Kc, as you all must be knowing. Kc will be simply equal to concentration of C at equilibrium, which is 0.2 ka square, divided by concentration of A at equilibrium, yes, which is 0.15 to the power 1 multiplied by 0.05 to the power 1, because stoichiometric coefficient is 1. Let me know the value of exact Kc which you are getting from here. Ashwarya is saying the Kc value is coming as 16 by 3. All right, Ashwarya, I go with you. Okay, Kc is equal to what? How much it's coming? It's coming 16 by 3. Now people, if I want you guys to write the units of Kc, what do you think? First of all, what is the value of delta Ng for the reaction? This is in gaseous form, this is in gaseous form, this is gaseous form. So 2 minus 1 plus 1, 2, 2 minus 2 is 0. So it is going to be unitless. ATM to the, moles per liter to the power delta Ng, since delta Ng is 0. Yes, since delta Ng is 0, so it's going to be unitless. Let me know in the chat box if it's clear to everyone. Yeah. Anish, you can talk to the operational team about it, bro. I have no idea about it. Yeah? I'm sure this is clear to everyone. Mohammed Abdullah, what's up? You are late, bro. Do not miss the sessions in between. Sony, it's simple. I told you the units of Kc. Units of Kc are going to be moles per liter to the power delta Ng. Delta Ng for this reaction is 2 minus 2, that is 0. If this value is 0, anything raised power 0 is 1, so Kc is unitless, yeah? Yes? Vishwajit, I have exactly no idea like what is this value coming out to be. Kirito, for this reaction. All right, guys. All right. I'm sure this is clear to everyone. This is the question which you guys are going to do, and let me know the answer of this question in the what? Let me know the answer of this question in the comment box afterwards. Take the screenshot of it and do let me know the answer of this question. All right. Now, people, in the tomorrow's session, we'll be doing the mole method for the reaction whose delta Ng is greater than 0, and we'll be doing this question. And with this, our today's session got over. Okay. The last 2 slides I'll be doing in the next session, which is tomorrow. Yeah. And people, let me tell you about the JEE 2021 crash course as well for the ones who joined us late. Let me tell you, we are starting the JEE 2021 crash course on the actual Vedantu platform, where you'll be personally mentored, personally trained by the Vedantu master teachers, right? We are going to cover your whole syllabus before your JEE 2021. If you are personally interested, you can enroll in this crash course and get trained properly, okay? And we will be conducting regular tests, assignments will be provided to you, everything. We are not going to left anything before your JEE 2021. We are going to do everything possible for the, before your JEE 2021 examination. Yeah. Now, people, how to get enrolled in this batch? How to get enrolled in this batch? Everything is here. You can check it out. You can check it out, guys. You can check it out. You have got over here one option: solve unlimited doubts with the doubt experts on our doubt app from 8 a.m. to 11 p.m. It's actually great, correct? And we are going to cover, which I told you already, cover entire JEE Mains syllabus as per the okay. And people, 10 full and 10 part syllabus tests to make your exam ready. Absolutely, okay. And at the same time, you'll be getting to know the amazing tricks and tips to crack the JEE Main 2021 questions in the power pack 90-minute sessions. Yes, Janvi, I'll be starting the GOC soon. All right, how to get enrolled in this, guys? There's a link in the description box for it as well. Just click on that link, use the coupon code as WSCC. On using the coupon code of WSCC, you guys are again going to get 20% off in this crash course as well. So if you really want to join, because I want you guys to join, okay, I want you guys to join this platform as well, where you'll be getting personal attention from the master teachers of your physics, chemistry as well as mathematics, who are going to train you personally before your JEE 2021. Yeah. All right, and people, there is one more link in the description box, which is for Telegram, as you all must be knowing. For the people who do not know, click on that link, guys. Get added to the Telegram group, okay, and stay updated about the classes as well. And do not forget to like the video, share the channel, and subscribe at the same time, so that everyone will get benefited out of these sessions. So, people, this was all from my side in the today's session. I'll see you guys tomorrow at the same time at 5:30, and tomorrow will be again the interesting session from the chapter Chemical Equilibrium. Till then, you guys take care. Bye bye. God bless you all. And love you all. Take care, guys. Bye.